Hey folks, Ms. Gosling here. In this video, you're going to learn about springs. By the end of the video, you'll be able to determine the force due to a spring using the spring constant. So let's go ahead and start by talking about springs. I'm sure you've all seen them. Look kind of like a slinky, like so. Now, the thing that's that's useful to know about springs is that they can expand and contract. So if I push on the spring, so if I apply a force in this direction, then my spring is going to contract, like so. I could also pull on the spring, pulling it to the right. And if I do that, the spring is going to expand. So, in both situations, the spring is being deformed, or it's changing shape because of a force being applied. We can use that change in shape to measure the spring force. The way that you did that in our lab, let me go ahead and clear my screen. The way you did that in the lab was by taking a spring and hanging different masses off of it. You measured the difference between how condensed the spring was without a mass and how condensed how condensed it was with the mass hanging on. And so we can see here what that difference is. By calculating the weight on the mass, you were able to see the relationship between the spring force and how far the spring extended. Now, when you did your lab, you probably noticed that the spring force, the force that you were applying to the spring by hanging a mass on it, and the amount with which the spring expanded or contracted had a linear relationship, like so. That relationship is written down in something we call Hooke's law, which you can see mathematically on the screen. So Hooke's law says that the spring force is directly related to the amount to which the spring either extends or contracts. So that F here is going to be the spring force, and X is going to be how much the spring expands or contracts. So how far it is from its equilibrium positions, its normal length. Now, I do want to mention this negative sign here. And this negative sign simply means that the force of the spring and the direction it is pushed in are opposite one another. So that means that, what I mean is that if this is my spring with a mass hanging on it, the spring is expanded down, right? So it normally might have this length here. So because it is being pulled down, that means that the spring force must be pointing up. So essentially what this means is that spring forces are always going to be in the opposite direction of any force that causes them to move. So in this case, gravity is pointing down and the spring force is pointing up. And that's why that negative sign is there. So the other thing I want to say is that this means that your spring force and X are always and how much it expands, or compresses again, are always going to have opposite signs. You can decide what those signs are, but it will always be opposite. So for example, in this case, in the case that I just drew, I would likely say that X was negative because X is going to be pointing down since it's expanding down. And the spring force is positive since it's pushing up. But again, I could flip that and we'll get the same thing. The last thing I want to talk about is this K here. K stands for the spring constant, And it is what we call a proportionality constant between X and our force. So what that means, so K has a bunch of different pieces of information added into it. The few things that can affect K are are the size of the spring, how big its circles, the circles in the spring are, each loop, how thick the material the wire is, what material it's made out of. All these things affect how springy it is, right? So you guys have pulled some springs are easier and some springs are harder to pull. And that spring constant is what defines what I like to call the springiness of the spring. So the bigger K is, the harder the spring is to pull. The smaller K is, the easier it is. So with all of that, let's go ahead and get started solving some problems. Example 1. A mass of 10 kilograms is hung on a spring. The spring extends out 0.4 meters. What is the value of the spring constant? So let's start by drawing a picture. So here is my spring, and it's going to extend out. Sorry guys, I am misdrawing this picture. Let me try one more time. So it's going to extend out 0.4 meters when a 10 kilogram mass is hung on it. And we want to find the value of the spring constant, K. So let's go ahead and do that. And I'm going to follow the guess method when I do this problem, even though I know it's a pretty simple problem. So I want to start by listing out my givens. I know that my mass is 10 kilograms and that my spring is extending out 0.4 meters. And I'm going to say that therefore X is negative 0.4 meters since the end of the spring is moving down. So again, that negative sign is directional, okay? Now I can go ahead and I can write out my unknown. And my unknown is my spring constant, K. So now it's time to figure out my equation. So I know that there's only one equation that has K in it right now. And that is that force is equal to negative Kx. But I don't have my force yet, right? I know that I know my mass, but I don't know my force. But I know that the force that is opposing my spring force is gravity. That is, if I were to draw the free body diagram for my spring, which I'm going to do up in the corner, my gravitational force would be pointing down, and my spring force would be pointing up. And because my spring is in equilibrium, it's not moving, I know that my gravitational force plus my spring force has to be equal to 0. So that is going to be my second equation, that my gravitational force plus my spring force equals 0. And I'm going to do one more step before I fix this. So I know that my gravitational force is mass times gravity, and I know that it's pointing down. That is going to be equal to, that plus my spring force is equal to 0. So that means that my spring force must be equal to mass times gravity. When I plug this back into my equation, that gives me mg is equal to negative kx. And now I am ready to substitute and solve. So I know that mg equals negative kx. So that means that my mass of 10 kilograms times the gravitational acceleration of 9.8 meters per second squared is equal to negative k times negative 0.4. Or 98 equals 0.4k, which means that k is equal to 245 newtons per meter. And there you go, I have solved for k. Let's do one more example before I finish this video up. Frodo hung a series of masses on a spring with spring constant k, creating the graph below. Find the value of k. So here is my force, here is my extension. Force, extension. Again, we're going to assume that they are in opposite directions, even though both are positive here. And the value of K, so we know that force is equal to K, negative K times X. And we're going to assume here that the force here is kind of the opposite of what our force should be. So we're going to go ahead and say negative of this force is equal to negative Kx. And that's because that's because this force measured on the y-axis is the force of gravity, not the spring force. So that means that our negatives are going to cancel, and you get the spring force is equal to K, or the force of gravity is equal to Kx. If I divide both sides by x, I get that K is equal to the force over x, or rise over run for my graph. So what that means is that K is equal to the slope or gradient in IB speak of my graph. So finding K is as simple as finding the slope of this graph. So K is equal to delta force over delta x. And I'm going to go ahead and just pick 2 points. I'm going to pick my first point and my last point. So it's equal to 4 minus 0 over 0.4 minus 0, or 4 over 0.4, or 10 newtons per meter. And there you go. That's my value of K from just a graph. So takeaways. First of all, the spring force follows Hooke's law, which we write as force is equal to negative Kx. And we can find the spring constant using a graph of force over spring extension. Specifically, K is equal to the slope of my graph. So there you have it, guys. This is all you need to know about Hooke's law. Go ahead, try solving some spring problems on your own. Best of luck and happy solving.